Hello, everyone. Today we're going to be talking about convergence of infinite series. So a series is just anything that involves adding up infinitely many terms and seeing what you get once you've done all of the adding. So here we're going to be looking at two examples of a series. The first one is the sum from n is equal to 2 up to infinity of 1 divided by n. So writing out the first few terms of the series, we have a half, plus a third, plus a quarter, plus a fifth, and so on. And the second series we're going to be looking at is the sum from n is equal to 2 up to infinity of 1 divided by n squared. So writing out the first few terms of this series, we have 1 on 2 squared, which is a quarter, plus 1 on 3 squared, so that's 1/9, plus 1/16, and so on. Now, you might be tempted to think that if we're going to be adding up infinitely many numbers, surely the result we're going to get is infinity. And sometimes that can happen, but that's not always the case. And it turns out that of the two series that I've presented here, one of them does go all the way to infinity once you've added all of the numbers up, but the other does not. So the question is, can you work out which is which? Well, let's have a look at the first one. The sum from n is equal to 2 up to infinity of 1 divided by n. Let's start writing some of the terms out. So we've got 1/2. I've decided it was appropriate to include this 1 here to indicate that we've got one of these terms. The next few terms, we've got a third and a quarter. I've decided to group them together, and there are two of these things that I'm grouping together. Next, we've got a fifth, a sixth, a seventh, and an eighth. And I've grouped four of these terms together. Next, of course, we can keep going. We've got 1/9 plus a 10th plus an 11th and all the way up to plus a 16th. And I've decided to group those 8 terms together. And we're going to continue on with this pattern. Now, what do we notice here? Well, we're not going to continue with equality anymore. Instead, we're going to deal with inequality. So this half, that's greater than or equal to half, so we just pull that half down. But what about this next pair of terms, a third and a quarter? Well, since 4 is bigger than 3, that means that 1/3 is bigger than 1/4. And so what that means is that we can say that this expression is greater than or equal to a quarter plus a quarter, and we've still got 2 of these terms. What next? Well, a fifth, a sixth, a seventh, they're all bigger than 1/8, so we can pull those down, and we've now got 4 of these terms. So 4 lots of 1/8. And we can continue on in this way with the 16th. We've got 8 lots of 1/16, and so on. What do you notice about all of these terms? Well, the half just comes down, but we've got 2 lots of a quarter, that's also a half. 4 lots of 1/8, that's also a half. 8 lots of 1/16, that's also a half, and we can continue on in this way. So the point is, no matter how deep we go into this series, we'll always be able to pull another factor of a half out. We'll always just be able to add another half to what we've got. And since we're just adding halves over and over again, that's going to be infinity. So this red sum that we've got here, the sum from n is equal to 2 up to infinity of 1 divided by n, this goes all the way to infinity. This means that this is a divergent series. Well, what about the other one? I said that one of these was finite, so it has to be the green one. Can we explain why this green series is finite? Well, let's start. The sum from n is equal to 2 up to infinity of 1 divided by n squared. Let's write out the first few terms. And instead of writing 2 squared, I'm going to write 2 times 2. Instead of writing 3 squared, we're going to write 3 multiplied by 3, and so on. 1 on 4 times 4, and we continue on in this way. Now, in order to explain why this sum is finite, we need to bound all of these terms from above, and it turns out that a convenient way to do that is as follows. 1 divided by 2 times 2. I'm going to say that that is less than 1 divided by 1 times 2. Since I'm making the number in the denominator smaller, that means that I'm making the overall fraction larger. So 1 divided by 2 times 2, a quarter, is less than 1 on 1 times 2, which is a half. That's certainly true. And I'll continue on in this way. With each of these fractions, I'm going to replace one of the numbers with one less than that number. So instead of 3 times 3, I'm going to say 2 times 3. And instead of 4 times 4, I'm going to say 3 times 4, and so on. So this expression that we've got here is at least as big as the green series that we're actually interested in. Okay, now you might be wondering at this point why even bother doing this? Well, there's a nice trick coming up, and the trick is as follows. For each of these fractions, we're going to express them as a difference of two other fractions. So for example, 1/2, you may notice that that's the same as 1 minus a half. So nothing too fancy going on there. But the thing is, you can also do it for the next term. 1 divided by 2 times 3, that's a sixth. And a sixth is actually the same as a half minus a third. So you can complete those fractions to see why that is true. And it's also true for the next term. 1 divided by 3 times 4, that's 1/12. That's also the same as a third minus a quarter. And it turns out that you can keep doing this for every single term in this series. Well, this is quite exciting now, because by simply removing the brackets, we can see something pretty extraordinary going on here. If we remove the brackets, we say we've got 1 minus a half plus a half, minus a third plus a third, and all of those cancel out except for the initial 1. And then we'll keep going. We have minus a quarter plus a quarter, that cancels, and so on. And the point is, you see that all of these terms cancel except for the first one. And so it turns out that this series is going to be no more than 1. So that means that this green series is actually finite. So it turns out that if you sum all of the 1 on n numbers up, you get all the way to infinity, but the same is not true when you sum up 1 on n squared. And in fact, you might already be familiar with this fact, it's pretty exciting, that we can actually compute what this sum is. If we sum all these numbers of 1 on n squared up from n is equal to 2 to infinity, that's a number that we're familiar with. It happens to be equal to pi squared divided by 6 minus 1. So this number is approximately 0.64493. So you might be wondering what's going on here. Why did a power of 1 fail? And why did a power of 2 give us something finite? Well, I'm not going to have time to explain this, but it turns out to be a general phenomenon. And in fact, there's a series test that you might be familiar with, which tells you exactly this. The test is as follows. If you're summing up 1 on n to the p for some p, and you're summing from n is equal to 1 to infinity, then this is actually going to converge. It's going to be finite if p is bigger than 1. But if p is equal to 1 or p is less than 1, it's going to diverge. So p is equal to 1 is the really, really special case that we just treated. This case is called the harmonic series, and we've just seen why it diverges, and we've also seen an example of convergence for a certain value of p greater than 1.